Okay, APE people. We're looking again at work, and there's a couple interesting things I want to make note of before we're looking at another example. The idea of how we measure work in joules. Okay. So, 1 joule. Is that a large amount of work, or is it a small quantity? What's the deal with this? Well, if you imagine average apple, right? An average apple has a weight or a force due to gravity of about 1 Newton. And if you consider that that weight, and if you lift this apple a distance of 1 meter, okay, then you've had to apply a force to it equal to about 1 Newton, equal to its weight, and you've moved that force parallel to a distance of 1 meter. You've done 1 joule of work. So it seems to be that 1 joule is really not a very large amount of work in terms of our everyday experiences. You can also check out in your textbook, page 192, table 7-1, for some more examples. There's another thing I want to consider, and what happens if you have a force, and the force could be small, could be quite large, but what if that force is applied but the distance is 0? Alright, well, you know that in the equation for work, force times distance, if you multiply anything by 0, you get 0. Well, okay, easy enough to understand. But the interesting thing is, imagine pushing on a wall of a building, and it doesn't matter how hard you push, it doesn't matter how long you stand there pushing, the wall is not going to move, and your distance will be 0. So, as tired as you get, you've done no work, according to the definition here for physics. And so there's another example. Imagine holding a suitcase or holding something as you stand around. Sure, your arm is going to get tired, no question of that. But if you're just standing there, if you're just holding an object stationary, the distance is 0, and you therefore are doing no work. Unfortunately, you're getting tired for no reason. So keep that in mind. Now, I want to consider again an example where we are looking at a force applied to an object, and the force is not going to be directly parallel to the distance traveled. So imagine what's going on here. We're going to have this horizontal surface, and imagine pulling a piece of luggage. Got a little wheel on it, low friction. We can, smooth, no friction. That's fine. And as you pull on it, you are typically going to be pulling in this direction with your hand on that handle. So if you're pulling on the handle in this particular direction with your force, then there are some things to consider. Well, obviously the luggage is going to travel parallel to the ground a certain distance, and our force is being applied at an angle theta to that distance traveled. So the luggage will end up over here, like so maybe. Okay. Well, there's another way of looking at what's happening here. We have our distance, and we have an angle here, and if we sort of approach viewing this as an angle part of a right triangle, we can see that we have a line of application of our force and the angle, and if we consider this angle, this distance to be the hypotenuse of this right triangle, then the right angle will be opposite of the hypotenuse. So what does this imply for us in terms of distances? Instead of looking at the force and two components of the force, we can look at distances and see what's going on. Well, with this right triangle, D represents the hypotenuse of the triangle. And so this distance from here to here is the side of the right triangle adjacent to the angle. This distance would therefore be D cosine theta. And this distance is the side of the right triangle opposite of the angle. So this distance would be D sine theta. And what this tells us is simply another way of looking at the equation for work, force times distance. We know that the force and the distance must be parallel. Well, we can either approach this from using a component of the force parallel to this distance here, and that would be the horizontal component of that force. Or we could approach this by looking at the entire force itself as traveling through this distance, which is going to be multiplied by D cosine theta. So what we have are two ways of looking at this. We could say that the force is parallel to D cosine theta, or that the component of the force, which is F cosine theta, is parallel to the actual distance traveled. Either way will give us the correct answer here, and it sort of doesn't matter which approach you take. And in math, you simply look at these two and you say, well, the order of multiplication really doesn't matter. Multiply force times distance times cosine theta, or force times cosine theta times distance, you get the same result. So we're fine in that regard. We could look at it this way, or we could say, well, I'm going to take the component of that force that is parallel to the distance traveled. Here would be D. And this guy here is F cosine theta. This being theta right here. Now there's an important thing to keep in mind, and we're talking about in the equation for work. Let's keep this in mind. Equation for work. Ft cosine theta. This angle theta will always have to be the angle between the line of the force and the distance traveled. If that angle shows up in a problem identified some other way, then you would have to make allowances for that and reconsider which angle you would use, what value of an angle you would use for theta in this equation. You'll see what that looks like right now. Let's see, this was page 4 in this sequence. So we're going to do a quick look at the same problem. But what if we're given some slightly different information? Our suitcase, okay, it's going to travel a horizontal distance here. We have our line of application of the force. And instead of being given the angle of the force here, we're told that that angle of the force is going to be measured as a certain angle away from vertical. My diagram kind of got crowded here, but all of a sudden theta's there. Well, okay. Here's F. If this is theta, well, we need to use an angle for our equation for work that is the angle between the force and the distance traveled, if this horizontal line represents that distance. Okay, so this is some other angle. You give it whatever symbol you want. I can call it alpha. And if we are given angle theta, then alpha equals 90 degrees minus theta. And it's no problem to go with that. And then we would use alpha, that value 90 minus theta, in our equation for work. Instead of writing theta, I would have to write alpha. And it's not an issue. It still works out just fine. A little more to consider with the angles here. And it's going to lead us to this idea that, well, not all work is going to be the same. You'll see what I mean in just a moment. There's the possibility of having positive work done. There's a possibility of having zero work done by a force. And there's also a possibility of having negative work done by a force. And the trick here is it depends on theta. It depends on the angle in between the line of the force and the distance traveled. So looking at the range of possibilities, if we consider that values of theta that result in cosine theta being a positive value, well, what that's going to give us is for cosine theta being a positive, well, we need values for theta that are greater than negative 90 degrees but less than positive 90 degrees. So if we have a theta of 0, well, cosine of 0 will give us a positive value. A theta of 40, cosine of 40 will give us a positive value. A theta of negative 78 degrees, well, cosine of negative 78 will still give you a positive value. What about zero work? Where would cosine of theta return a value of 0? Well, in that case, theta has to be equal to either positive or negative 90 degrees. Cosine of 90 degrees is 0. Cosine of negative 90 is also 0. We're going to finally look at situations where we have cosine of theta returning a negative value for us. And for this situation, we need theta itself to be greater than 90 degrees, but we need it also to be less than 270 degrees. Now, why that? Why doesn't it go all the way up? Why does this set, positive, 0, negative, not encompass 360? Where would 280 degrees, 290 degrees fall? Well, 270 degrees is the same as negative 90 degrees. So we actually have looked at the entire circle, if you will. All angles are considered in these sets. So if theta is actually equal to 270, well, then that means it's actually equal to negative 90 degrees, and that would give us 0 work. So less than 270, but greater than 90, and we're in that range. If you look at a set of coordinate axes here, okay, for cosine positive value, we have anywhere from negative 90 to positive 90, but exclusive of those two values. So we have from there to there. Cosine of 0, where we have actually theta equal to positive or negative 90, and that's easy to show. it would just be either straight up or straight down for the value of theta. These arrows here are not representing vectors necessarily. We're looking at an angle itself. So if you notice now that here at positive 90 or negative 90, we're going to be producing an angle between the distance traveled and the force that's 90 degrees either way. The two things we're considering, force and distance, are perpendicular to each other in this sense. And so anything perpendicular results in zero work being done. Now for cosine returning a negative value from 90 degrees to 270 degrees, but again exclusive of those two values, basically we have this side, any angle on that side of the y-axis as measured from, I should say, as measured from the positive x-axis, right? If we have a particular angle, let's say 140 degrees, it would be somewhere over here, roughly, then that is an angle measured from the positive x-axis, of course. And here, let's say we're looking at an angle of negative 30 degrees. Okay, well this is an angle measured from the positive x-axis this direction, clockwise. A counterclockwise measurement would be a positive measurement for an angle. A counterclockwise measurement this way, clockwise measurement this way is a negative value for an angle. Counterclockwise is a positive value for an angle, just as an example. So here we could say, well, we've got positive 90 degrees or negative 90 degrees. Here we have anywhere in this range, and here we have anywhere in this range. This was page 6 in this sequence. All right, so we have those examples. Now, this is kind of an interesting thing. What we're looking at is the idea that work can be positive. Well, work can be zero. You can have zero work done by a force. Work can also be negative. Now, we learned early on that work itself is a scalar quantity. It does not have a direction to it. But you will have to consider positive and negative work at different times. And so remember the example of the suitcase. We're going to come back to that one more time, and you'll see why in just a moment. So check this out. This is page 7 in our sequence here. So with this example of the suitcase. Handle, wheel. Okay, we are applying a force in this direction. The distance traveled will be horizontal, and we'll have an angle theta here. Okay, fine. So we're going to consider the work done by the applied force. And I'm going to add some notation here. The work done by that applied force. Well, that's going to be pretty easy. That's going to be the force applied times the distance traveled times the cosine of theta. Let's add some numbers here. Let's say we are moving the suitcase through a distance of 8.5 meters. Let's say theta happens to be an angle of 43 degrees. And our force applied, well, why don't we call that a force of 32 newtons? Okay, so we have some numbers we can plug in. No problem. Force applied was 32 newtons. The distance traveled, 8.5 meters. Let's say it's a large room we have to cross with our suitcase. Cosine of theta. Theta would be 43 degrees here. All right. So it's quite easy. We can see that our angle theta is going to be less than 90 degrees. And so from this bit being less than 90, but also greater than negative 90, well, that should indicate we get a positive value. Should be no problem. The cosine of 43 turns out to be 0.73 and change. And we can multiply it by 8.5 and 32. Work done. Oh, if we go with 3 sig figs, it rounds to 199. Almost wrote newtons. Well, it would be newton meters, wouldn't it? Force times distance, newtons times meters. But that equates to joules. 199 joules of work being done by the applied force. Now, we all know about the real world, lots of friction everywhere around us. What if this force we are applying is not accelerating our suitcase? What if the suitcase is in equilibrium and its acceleration is 0, and therefore the net force acting on the suitcase is 0? Well, we're still doing work. We're still applying a force across a distance. That's not in question here. But is the work we are doing with our applied force the only work getting done on the suitcase? And the answer has to be no, it is not. There will be another force, and of course the force is friction. Let's say the friction is down here in the wheels. That friction is going to oppose, it'll be kinetic friction, and it's going to oppose our motion. And now the next follow-up question is going to be, how much work does this force do? Well, we have to figure out how large that force is going to be. And we will then multiply that force by the distance by the cosine of theta between those two items. We come back to Newton's second law of motion, sum of forces. And since we know no acceleration, net force is 0, that when we add the forces together, the sum will be 0. But I have to consider really just the horizontal direction. Our friction is in horizontal direction, and I have a component of force in the horizontal direction. So sum of forces in the x direction. And so I have the component of this applied force. Well, that's going to be force times cosine of theta. It's adjacent to the angle theta here. Force applied times cosine of theta. And in the negative direction, I will end up having my friction force. So minus force of kinetic friction. And that sum is 0. Okay, fair enough. So what that tells me is that my applied force times cosine of theta is equal to the force of kinetic friction. Awesome. And I can work this out, therefore I can find the value of my kinetic friction force. So my applied force is 32. I'm going to multiply by the cosine of 43 degrees. And the amount of friction here is going to be in 3 sig figs, 23.4 newtons. Awesome. And that is a force applied in the negative x direction, but my distance traveled is in the positive x direction. So if I look at what's happening here, now for the work done by kinetic friction. I'm not going to set up an equation just yet. I'm going to actually just have a quick sketch. I have the distance traveled in the positive x direction. Here's distance. I have the force applied in the negative x direction, kinetic friction force. The angle between these is going to be angle theta, and I can see that theta is going to be equal to 180 degrees. Okay. So that tells me something. Coming back to this information, where theta is 180 degrees, that puts me in greater than 90 and less than 270. So I should get a negative result here. The work should be negative. So let me set up this equation here. The work done by the friction force is the friction force times the distance traveled times cosine of the angle between those two. Cosine of that angle. So, work done by the kinetic friction force. The value here was 23.4 newtons. the distance traveled is still the same distance, 8.5 meters. And cosine of theta, theta is 180, so cosine of 180. Just to verify if my memory is not working so well, I do cosine of 180 and I get a value of -1. Okay, then I multiply by my force, 23.4, and multiply by distance, 8.5, and I get a negative answer. And with rounding to 3 sig figs, 199 Newton meters, which comes to joules. Now it's very important to make note of this. Okay, finish this up. Work done by the force of kinetic friction. Look at this. Is that a coincidence? Well, no, it's not. I had the suitcase in equilibrium. There was no net force. The sum of forces was 0. The friction force was completely canceling the horizontal component of the applied force. Now, my applied force did do work on the suitcase. Friction also did work, and it did negative work. Well, what does this mean for us? We can actually talk about the total work done on the suitcase. And all we have to do is look at the sum of all the works done by all the forces. Anything happening vertically here? Well, there was no distance traveled vertically, so there was no work done vertically. We can clearly just see that, and it's just a statement we can make. But for the sum of forces, for the sum of the work done, we have the work done by the applied force, and we would add the work done by the force of kinetic friction. And in this case, we are getting 0 when we add those two together. They completely cancel out, which is going to be a little interesting, a little hard to swallow, since work is a scalar. It does not have a direction to it, but you can cancel positive work with negative work. You can. That is valid. Okay, enough on this one for now. Thank you for watching, and I will see you next time.